Newton's laws, we were discussing about pulleys and tension being uniform in a massless string or a light string. So let's continue the analysis from that point onwards.
Yes, sir.
So there was also again today lecture of NLM at the morning.
Yes, you had a cover-up lecture, no?
Yes.
So what are the things that you have covered in that lecture?
So those who are of Indigo house from first for their which is not done now, which is left now for IIT chapter. I think so that is done.
Okay, okay.
No, sir. In today's session.
So that was cover-up lecture. Okay, so that is independent of this thing. Okay. We will just continue from where we left off in the last lecture, which was the third lecture. Right. So we were talking about, first of all, tension in a string or rope or chain or whatever. So one thing we had understood that for what is called a light means of negligible mass. So for a light thread, the tension is always uniform. That is the same at all places. Whereas for a heavy rope or chain, the tension may be variable. So it may be non-uniform. So let us once again understand this with two examples. So in one part of this example, what we have is two heavy blocks, but attached by a very light thread. On a massless, on a frictionless surface, and we are pulling this with a force F like this. Okay. And on the other hand, we have another case where rest of the things are the same, but it's a heavy rope in between the two blocks. So let's say the heavy rope has mass M. And again, this system is also being pulled from this side with a force F. And of course, this is also a frictionless surface all the way. So in this case, mass of A is given to us as 2 kilograms, mass of B is given to us as 3 kilograms. And the force we are applying is, let's say, 5 newtons. So find the tension in the string and show that it is uniform at all points. And in this second case, let's say mass of the block A is, this time, let's say 7 kgs. Mass of the block B is, let us say, 11 kgs. And mass of the rope is 2 kgs. So small m is 2 kgs. And the force we are applying is 20 newtons. So find the acceleration of the system, and the tension at each end of the rope and also the tension at the midpoint. So through these two questions, we will illustrate that tension can be variable in the case of this thing. Yes, that's correct, Ritesh. Okay, so just work this out quickly and send me the answers. Okay, so anybody else apart from Jitesh who has got the answer for the first part? Here you should be getting the tension in the string as 2 newtons. Okay. And I'll show you how to prove that it is uniform, but the first part, the tension will come out to be this much. Okay. Now in this case, if the tension at this end is TA and the tension at this end is TB, then we
Sir, how did you find it is 2 newtons?
I'll explain. Try it yourself first from the free body diagram. Okay. Here also tension at this end will be 2 newtons. Okay. Sorry, tension at this end will be 7 newtons. But tension at the other end, TB, will be greater than 7 newtons, you will see. It will be 11 newtons. You just make the free body diagrams of the individual blocks and you will get this. Yeah, so basically we are just looking into a particular problem which is stated over here to clarify this point that the tension in a string, okay, if the string is massless versus if the string is a heavy rope, how to deal with the two situations. So I haven't shown the solution step by step of this question yet. You are supposed to make the free body diagram in each case of the blocks A and B and of the rope or string, whatever required. And from that, explain these points, okay? So those who have just joined in from non-integrated batch 2, don't worry about the few minutes you have missed out. It'll be there in the recording, and plus we've just started with this, so I'll explain this from the beginning. Just understand the question, both the parts that I've asked away. We'll discuss the solution soon. I've given the answers here for you to verify. Just understand the question. I'll be discussing the solution soon. Okay, so let's understand each part in detail now. So in the first part, your individual blocks were of mass 2 kgs and 3 kgs, and the string in between them was massless. And we are pulling with a force of 5 newtons. Now this is a massless thread. Okay. So when you make the free body diagram for block A, you can see that if the tension at this end is TA, actually you know that TA should be equal to TB because it's a massless thread. Okay, but even if you assume that the tensions are different, you'll be able to show that the values are ultimately the same. So this is for the block A. Then for the thread, if you make the FBD, then at this end the tension is TB, at this end the tension is TA. The thread is also accelerating, but its mass is tending to 0. It's massless. And for the block B on this side now, there is force F, there is TB, it should have the same acceleration. And of course, weight is supported by normal reaction. So you just need to write the horizontal equation. So we have F minus tension is equal to mass of B into acceleration. We have tension at B minus tension at A is equal to 0 because mass is 0. And we have tension at A is equal to mass of A into acceleration. So this equation here is showing us that tension at B is equal to tension at A. It shows us that there's a uniform tension, say P, in the massless thread. Okay, so this is the second part's proof which I told you, that show that the tension is uniform. This is the way to show that. Okay, so this equation therefore converts to F minus P is equal to mass of B into A. And this equation converts to T is equal to mass of A into A. So this is 5 minus T is equal to 3A. This is equal to T is equal to 2A. So if you add these two equations, you'll get the acceleration as 1 and you'll get the tension as 2 newtons. Okay, so this is the solution of the first part. Now use the same kind of method for the second part, but the difference is in the second part. Obviously, mass of A and B is different, F is different, but the main difference is that the thread is not massless. It is a heavy rope. So the rope itself has a mass of, I think it was 2 kilograms, right? So I'll just copy paste this here below, okay, so that you can work on the free body diagrams of the second part yourself. Once you've done a run through of this part. Okay, same method, but the slight technical difference now is in the second part. The rope is heavy. Okay, so now as you can see, for this type of situation, when we make the free body diagrams of each of them, for the block A, for example, there is only one horizontal force, TA, which is giving it the acceleration A, which is the same as the common acceleration of the system. Okay. Vertical forces, I'm just showing in the diagram, but they balance each other, so they're not really important. So tension at the point A, at the end A of the string, should be equal to mass into acceleration. This is my first equation. But now when I make the heavy ropes free body diagram, I have to take into consideration that it itself has a mass m. Okay. And that is also moving with the same acceleration A. So that is why the tension at the point B will be greater than the tension at the point A, because net force, which is mass into acceleration, is not zero now, because m is not zero. So that is the major difference between these two cases, the heavy rope case versus. Okay. Now, in case you're also wondering what is balancing the weight of this rope, you'll understand that there'll also be some kind of a reaction force which acts like this. Okay, the rope is also pulling down these two blocks. So these are like reaction force at the point where the string is joined to the block. Okay, so that is also there. But again, those are balancing, so it's not important for us. Okay. Now this block B, on the other hand, is experiencing F from this side and tension like this, and it also has the same acceleration E, and its weight is balanced by normal reaction. Actually, there will also be a reaction force acting like this here. But as I said, vertical forces are not going to play a role in this problem because they are balancing. This is my third equation. So when I list together the equations, equation 3, it becomes F minus tension is equal to 11A. Okay, then equation 2 becomes tension at B minus tension at A. It's equal to 2A, and equation 1 becomes tension at A is 7A. So now we can just add these three equations. So F on this side will become 11 plus 2 plus 7A. So we see that the acceleration becomes F by 20, or 20 newtons divided by 20 kgs. So once again, in this problem also we're getting the acceleration's magnitude as 1 meter per second square. And once you got that, from that we can calculate the tensions. Okay. So we can put these back in these equations, and we can see that from equation 1, tension at the point A will become 7 newtons. Then from equation 3, you can see that tension at the point B will become 9 newtons. Or you can use equation 2 also. Okay. Now the only thing remaining is, so these are the tensions at these two ends. Now we also want to find the tension at the midpoint C, let's say, of the rope. So we'll discuss about that next. But first, just go through this and make sure these free body diagrams and the corresponding equations are clear. Ask me if there's any doubt with it.
Sir, we are yet about to find tension at C, no?
Yes, that we have to do. But I had given you the value in case you tried it yourself. The value will come out to be 8 newtons. I will show you the method, but try it yourself if you finish this.
So can we say tension at C is the average of tension at A plus tension of
Yeah,
B?
it comes out to be that. Okay, it comes out to be that also, but the technical reason is actually again free body diagram. Okay. Why it comes out to be the average is because mass is uniformly distributed for the rope. Okay, so you'll understand that when we make the free body diagram. So now let's look at that part. Okay. So suppose this was the free body diagram of the entire rope. It's of mass m and length L, and this is the midpoint. And at this point B, it was being pulled with force equal to the tension at that end, and here it's being pulled back with the force equal to the tension at this end. At this acceleration E. Now imagine that you're mentally cut this rope in two parts, and you're separately making an FBD of this part AC and separately making an FBD of the part BC. So because the mass is uniformly distributed, so each part will have a mass of m by 2 because each part has a length of L by 2. So C is the midpoint. So I just mentally cut it into two parts, and so this is being pulled with a tension TB, but this is being pulled back with the tension at this point. This is being pulled forward with the tension at this point and being pulled back by tension at this point. And these two halves also have the same acceleration. So for the above FBD, we had the equation that TB minus TA was equal to MA. But for this one now we have the equation that TC minus TA is equal to M by 2 into A. And for this one, we have the equation that TB minus TC is equal to M by 2 into A. So if you compare these equations, you'll be able to show that. So comparing with the equations, you'll be able to show that equation 1 is equivalent to equation 2 plus 3 on the right hand side. Okay. So TB minus TA is equal to TC minus TA plus TB minus TC. But also, you'll be able to compare and show that tension at the point C will be the arithmetic mean of the tension at the two ends. Yes, I'll scroll up. Okay. This was how we found the tension in the midpoint of the rope. And earlier we had found the tension at the two ends of the rope, A and B, like this.
So can you slide a bit down?
Yeah, I will slide down. Let people finish with this part first. I'll come down in a moment. Okay.
Sir, how did you get the formula TC is equals to TA plus TB by 2?
You have to just substitute. Okay, so for example, in this equation, from this equation, A is how much? TB minus TA by 2 m, sorry, by m. TB minus TA by m. Now substitute this in either of the two equations. Substitute in either equation 2 or equation 3, and you will get this result. You will get this result.
So,
Yes.
so I had a doubt, like, how did you came to that equation, like TC equals to TA plus TB by 2?
Exactly. So what I've done now, from the first equation, I have calculated the value of A in terms of TA and TB. That is this over here. And then I've substituted that in either the second or third equations. Just substitute the value of A and you'll get this. Understood? No? So on doing this
Sir.
substitution, you will get this result.
Yes, sir, got it, sir.
Okay.
Sharing the screen.
Sorry, but I couldn't hear you. Is this any question? Any doubt?
I'll share the screen.
Unfortunately, your voice is not coming clear. So you can also text message me any doubt that you have. Okay. Now, next, we'll move on to systems with pulleys. Oh, okay. Okay, we'll go back to that. Finish writing this. Then we'll come to. Okay, so before we end up with this, yeah, so Siddharth, that is true. From these equations, you can see that whenever we have a heavy rope, as long as the mass is uniformly distributed, okay, which is always the case actually. So the tension at the midpoint will always be the average or the arithmetic mean of the tension at the two ends. Okay. But of course, if it's a light thread and its mass is tending to zero, then the tension is uniform everywhere, which you can understand from these equations also. Okay. So now moving on from this, the next thing, pulley-based systems. Now in pulley-based systems, we will always use massless threads. We will not have a situation where heavy ropes are used in a pulley-based system. It will always be massless threads. So whether or not given directly in the question, you should assume by default that the thread used is very light or massless. And also, as we have discussed in the last lecture, the pulley's surface is smooth and the pulley itself is fixed in such a way that the thread going around the pulley slips on it without any friction. Okay. So this is our first example of a pulley-based system for today. Okay. So this is a light, or what we call massless, and also inextensible. So that means it cannot stretch. It's not like a rubber band. Okay, it's like a regular thread. So it's an inextensible thread. So if it cannot stretch or it is inextensible, it means that it is of fixed length. That kind of rope is used. There are two blocks attached like this. This is a smooth fixed pulley. Okay. So what will happen is, assuming that mass of A is heavier than mass of B, suppose that is given to us, then the moment we release this system, because of the additional weight that A has compared to B, A will tend to accelerate downwards and B will tend to accelerate upwards. So once the system is released, because of the weights of A and B pulling them downwards, the string will develop a uniform tension. But because mass of A dominates over mass of B, A will accelerate downwards. So when released from rest, in such a system, A and B's weights pull them down, creating a uniform tension T in the thread. And because A's weight is greater than B's weight, so A accelerates downwards and B accelerates upwards. This is what happens. So suppose in a problem like this, we are given the mass of A's value, the mass of B's value, and acceleration due to gravity as 10 meters per second square. And we want to calculate the acceleration, okay, and the tension in the thread. So ultimately what we will use is the free body diagram method to calculate this.
Sir, can you reread the statement?
Okay, when released from rest in such a system, A and B's weights pull them down, creating a uniform tension in the thread. And because the weight of A is greater than the weight of B, A accelerates downwards, whereas B accelerates upwards.
So can you please read the point again?
Okay, so now let's understand how we'll deal with the question. Yeah, don't worry about the point. I have explained it twice. Just you can access it later. Okay. So
But I'm right.
yes, okay, you can write it down from the notes later. Let's understand the method of solving. That is the more important thing here. So what is happening is that if you look at the free body diagram of the block A, okay. So on it, what forces are acting? The tension in the string is acting upwards, and the weight is acting downwards. And because this is going down, so obviously the weight is going to be more than the tension. Okay. So the free body diagram of the block A looks like this. And from this, the equation that we'll get when we solve is that net force is going to be equal to mass into acceleration. Okay. So in this case, the net force will be 30 minus T is equal to 3A. That's our first equation. Okay. So if you just compare this free body diagram from the diagram above, you'll understand what's happening here. So the moment we release this system, A's weight is pulling it down. B's weight is also pulling it down. So that creates the tension in the thread. But because A's weight dominates, okay, weight of A is 30 newtons, weight of B is only 20 newtons. So this one dominates. So that's why A ends up accelerating downwards. And because it's attached by a thread, B gets pulled upwards with the acceleration A. So now to solve for that acceleration and the tension, you have to just make the free body diagrams, okay, as explained in that point. So free body diagram of the block B look very similar, but the only difference is that it will be accelerating upwards. This will be accelerating upwards. So now I want you to try and write the equation yourself for this one, okay? And then solve the two equations that you will get to find out the acceleration. Khushi, just check your answer again. It's not correct, okay? Write the similar kind of second equation and then solve these two equations to find the tension T and the acceleration E. Okay, so what is happening here is in the case of block A, you can see that it's accelerating downwards. So the net force should be in the downward direction. Our axis should be pointing down. That's why we have written the net force as weight minus tension is equal to mass into acceleration. It's very simple. The
In the
direction of
B's
net
case, it
force.
will be tension minus weight is equals to mass
Yes.
into
Yes.
acceleration.
You write the equation and solve yourself. Okay, send me the answer. I'll verify it for you. Yes, but what you're saying is correct. So you should always take the direction according to the direction of the acceleration. So if it's accelerating upwards, then the net force should be in the upward direction. Right. So let me check the answers you people have sent. Yes, very good, Ayan. That's correct. And Khushi, your answer is also correct. Very good. Siddharth, correct. Okay. So this equation will, because this is accelerating in the upward direction, so we have to take the net force in the upward direction. So T will come with a positive sign and the weight of B will come with a negative sign. And that is equal to mass into acceleration. So this equation numerically becomes P minus 20 is equal to 2A. Now, if you just add these two equations, 30 minus T is equal to 3A, P minus 20 is equal to 2A. You just add these two equations, you'll see you'll get 10 is equal to 5A. So from this, you'll get acceleration equal to 2 meters per second square. And then substitute that back in the equation. So you'll get tension equal to 24 newtons. You can substitute it in either question, either equation, 1 or 2. Okay. So it's very important to understand the direction and the sign convention in each of these three body diagrams, because we know for sure that A is accelerating downwards and B is accelerating upwards. So when we write net force is equal to mass into acceleration, in case of A's free body diagram, we consider the net force in the downward direction. And in the case of B, we consider the net force in the upward direction. So tension comes with positive sign and weight comes with negative sign in the case of B.
Sir, can you explain me the equation 1?
Yeah, equation 1 is the net force acting on the block A. A is going down. So there's a downward force equal to its weight and the upward force of tension pulling it up. So what is the net force? It is weight minus tension. So that should be equal to mass into acceleration.
Okay, sir, thank you.
Only two forces acting on it and one is dominating over the other, that is the weight. So the net force is weight minus tension. Okay, so hope this is completely clear now. Okay, this question. Now let's see another example of a pulley based system. Now next we'll see a situation like this. We have a frictionless tabletop kind of thing. And at the end of or at the corner of the table here, we have a smooth pulley fixed to the table. Like this. Okay. And a thread which is attached at one end to a block which is hanging vertically like this, and the other end attached to another block which is placed on the smooth surface. So here it is given that the mass of block A is equal to 4 kilograms. The mass of block B is equal to 6 kilograms. And acceleration due to gravity we have to take as 10 meters per second square. So again, find the acceleration of block A and B and the tension in the thread. And we will consider this to be a smooth fixed pulley, okay, which is also negligible in mass compared to the blocks A and B. And this one, as usual, is a massless and also inextensible thread. So to find the tension in the thread, and we also have to find the reaction force acting on the pulley through its hinge. That is, the pulley is hinged to the table through a support like this. So at that hinge, you'll understand when you make the free body diagram, there is some kind of reaction force acting. So how much is that reaction force we have to calculate? Okay. So take down the question and start by making the free body diagrams of A and B, okay, and write equations for A and B. Equations of the type net force is equal to mass into acceleration, that type. Okay. Start with this and then we'll see that solving these, we will be able to get the acceleration A and the tension T in the string.
Sir, what is that written reaction force acting on a pulley through its?
Hinge, Hinge, hinge. Yes, Khushi, your answer is correct. For the acceleration. Siddharth and Nayan, unfortunately, your answers are not correct. Anyway, we will just first understand the question a little bit more. Yes, Ethan, your answer is correct. Very good. So what happens is A's weight is pulling it down, and that is what creates tension in the thread, and that tension will act uniformly in terms of magnitude at all points. Of course, B's weight does not play a role in this part because the string is horizontal, and therefore A has to pull B horizontally as it goes down, and the magnitudes of the acceleration is same. So this will be the overall situation. Now to get the values of all these, we just need to make the free body diagrams. So for the block B, you can see that no resolution, all that is needed. It's a very simple situation. It's having a horizontal acceleration E. And for block A on the other side, it's even simpler. It's having a vertical acceleration A because only two forces are acting, out of which the weight is dominating. So for this, we have the equations along the horizontal. We have T is equal to this, okay. And along the vertical, we have N minus the weight is 0. Okay. So this equation, in fact, is not needed also because it just tells us normal reaction balances weight. For this, just a single equation is required for the vertical downward direction. Weight minus tension is equal to mass into acceleration. So this is our second equation. So now with the values, you can see the first equation becomes that T is equal to 6A, and the second equation becomes 40 minus T is equal to 4A. So adding the two of them, you will get 40 is equal to 10A. And then T is equal to 24 newtons. So this is this part, okay. Now the only thing that is remaining is the reaction force at the hinge. The reaction force on the pulley. How do we calculate that? So for that, what you do is you think of the free body diagram of the pulley. So on the disc of the pulley, what is happening is that from this side, there is a vertically downward tension acting. On this part, there is a horizontal tension acting. And of course, it's massless, so it does not have any weight of its own. But these two are pulling it together in this sort of direction. So there has to be some reaction force which acts like this. Okay, so if you show these forces, and this is at rest, the pulley is at rest. So net force should be 0. Okay, so if you just show it as a point mass, it becomes even more clear what is happening here. These two tensions are acting like this. So the net force must be 0 in this case. Okay, so solve that to find the value of reaction force and substitute the value of tension from here. Okay. Yes, very good, Rishita. That's correct for the reaction force. So here you can see that we have this kind of symmetry. This will be at 45 degrees because this angle is equal to this angle equal to 45 degrees. So the reaction force will have a magnitude of T root 2. So it will be 24 root 2 newtons, or you can approximate it as 24 into 1.4 newtons. And it will act like this at a 45-degree angle, as you can see.
Sir, can you explain the concept of reaction pulley again?
See, on the disc of the pulley, there is one tension which is pulling it down like this, one more tension which is pulling it like this. So these two together are pulling it in this sort of direction. Understood? No? Like this. So that is pushing it against the hinge. No? So the hinge is reacting by applying a reaction force which is equal and opposite. No?
Okay,
Is
sir.
it clear
Thank you,
now?
sir.
No? Just like, for example, in the previous case where we had the pulley attached to the ceiling like this, there it was like this. Okay, so there was tension like this and tension like this. Now in this case, if you want to calculate the reaction force, it's that much simpler because both of the tensions are vertical. So this, the two ends of the thread, they are pulling the pulley downwards like this. Okay, and at the hinge there must be some reaction force which is preventing this from going down because this is at rest. So here the reaction force would have been 2T, okay, in this example. But in this example, because the thread is not like this, the thread is, one section is horizontal and one is vertical. So the tensions are acting like this and not like this. Okay. So here the reaction force acts along the bisector at 45 degrees and its magnitude is equal to T root 2. So this was the important thing to understand in this. Okay. So this is clear to all of you. Okay, now let's do one more problem of this type for practice before we move on to another section of application of Newton's laws. So this time we'll see a slight variation of the previous situation where instead of a horizontal tabletop, we have an inclined surface where this angle of inclination is 37 degrees and this is a smooth surface. Now on this we have a block like this. The thread attached again with a smooth fixed pulley on this side, and the other end of the thread, which is vertically hanging, is attached to another block D like this. Okay. Now all the things are standard, so it's the thread is massless and inextensible. Okay. The pulley is smooth and fixed, and mass of A is equal to mass of B, is equal to, let's say, 2.5 kgs each, and G is equal to 10 meters per second square. So again, we have to find their accelerations. Okay, then the normal reaction on the block E, and we have to also find the tension in the thread. Okay, so try to work this out quickly. The method is the same. You make the free body diagram of each of the blocks and solve the equations for net force is equal to mass into acceleration. For that, you will get these values. Okay, I'll just put up the answers. So you will get the acceleration as 2 meters per second square. And therefore you will get the tension as 20 newtons. And the normal reaction acting on the block A, you will get that as 20 newtons also. So both of them have the same mass. So it's quite easy to navigate this problem. So when you make the FBD for the block A, it's moving along this surface with an acceleration A. So you can take this as our x-axis and take perpendicular to this as our y-axis. So when we resolve the forces and show it, the weights components will be mg cos theta and mg sin theta. And the normal reaction will be like this. And the tension in the thread will be like this. Okay, so let's look at the resolution of the weight once more acting on A. So you'll see that on the block A, the weight is a force that is acting vertically downwards. And we are considering our x-axis to be along the inclined plane and our y-axis to be perpendicular to the inclined plane. So with respect to the horizontal direction, this is theta. So this angle also becomes theta. And that is why when you look at the components, this one becomes mg cos theta. And this one becomes mg sin theta. So your vector algebra should be very accurate in such situations. Inclined plane we have discussed in previous problems also. So this is the free body diagram for E, and this will give us the equation. Along the x-axis we'll have T minus mg sine theta is equal to ma. This equation becomes T minus 2.5 into 10 into 3 by 5 is equal to 2.5 E, or T minus 15 is equal to 2.5 E. And along the other direction, we have normal reaction balances mg cos theta. So this will tell us that normal reaction is equal to 2.5 into 10 into 4 by 5. Normal reaction is equal to 20 newtons. Whereas this is our equation 1. Now, when you look at the free body diagram of the block B, it's very simple. Tension acting upwards, its own weight, which is the same as the weight of A acting downwards, and it has a downward acceleration A. So for this block, we have the equation that mg minus T is equal to ma, or 25 minus T is equal to 2.5 E. This is our third equation. So now solve equations 1 and 3 to find E. And you'll see you'll get the value of A as 2 meters per second square and the tension T as 10 newtons. As 20 newtons. So the key thing in this problem was the resolution of the forces properly for the inclined plane situation. So make sure you're clear with that. Just a moment, I'll share the screen again. Yeah.
Sir, in this case, what will be the reaction force acting on a pulley?
That you will have to calculate because the tensions will act at a certain angle. So you have to calculate the vector sum of those two using the diagram, and then the reaction force has to balance that. You see that the angle between the two tensions acting will be in this case 53 degrees, and the tension's magnitude is 20. So you have to add the two tensions with the angle being 53 between them using the triangle law. Okay.
Okay, sir.
Okay, so hope the solution of this is completely clear now. So solving these two equations, you can see you will get this relation. You have 25 minus t is equal to 2.5a and t minus 15 is equal to 2.5a. So just add these two equations. Okay. So you have a is equal to 2 meters per second square, and then substitute in the above equation, so you will get tension as 20 newtons. Okay. So in this particular question, I did not ask for reaction force, so you can leave that out. It's not necessary to calculate. You can just. Okay. So we got the tension in this, and we already got the normal reaction as 20 newtons. So these three things have been asked. Okay.
Sir, in the last sum, I calculated the reaction force with the resultant of the both the forces with the minus sign, but I didn't got the same answer.
Which question are you talking about, Vinay?
Sir, the previous one, previous to this one only. The last one that we solved the resultant force. So I took both the t's and used the rule t square plus 2t cos theta 1. I used
Yeah,
that
so
formula and then
the angle
just
here is how much is 90, na beta? So you'll get t root 2 only as the answer. Cos 90 is 0, na beta?
sir, I think I took the angle 45 only directly. Sorry,
No,
sir.
but the angle between the two tensions, you can see is 90 degrees. Na? Okay, so have you understood that now?
Yes, sir.
Okay. So these are the first level of questions for pulley systems where there's a single pulley. Now we come to the next level of systems where we have multiple pulleys. More than one pulley. So in this we'll see that there is something called constraint relations. Okay. So let me explain with an example. So suppose we have a situation like this. Again, a horizontal smooth tabletop, okay, with a pulley here, but there is another pulley in our system such that this is a pulley fixed to the corner of the tabletop, okay, but the other pulley is actually attached to a block, okay, and the thread is going around that. So this pulley is actually attached to another object here. Let's say A. Okay. And then this is attached to another object, let's say B. Here this is attached to a fixed ceiling. This is a smooth surface. So in this also what will happen is that because of the weight of A, it will tend to slide down, or it will tend to come down, and that will pull B horizontally like this. But what we'll see here is that the acceleration of A will not be equal to the acceleration of B because the thread is going in a more complicated way here. So in such an example, there is a relationship between acceleration of A and acceleration of B. In fact, there's a relation between the motions of the two blocks. And that relation is called a constraint relation. So the term constraint, it actually means a limitation or a boundation or like a fixed rule. So this system has to follow a fixed rule. So that constraint basically comes from the fact that the thread length has to be conserved. It's a fixed thread length. So this constraint that the system has, that the thread cannot stretch because its total length is fixed, that determines the relationship between the acceleration of the block A and the acceleration of the block B. And secondly, you can see that it's a massless thread again. So tension acts like this. So now let us understand what this constraint relation is exactly. Okay. So just make a note of this diagram first, then I'll explain to you the constraint relation. Okay, so now this is something very important, so pay close attention. So if we look at the system, how the motion of the two objects progresses with time. So we'll understand the type of constraint that is involved over here. Now initially, let's say when the system started its motion, the situation was like this. This was our block B, this was our block A. Now let us say that this distance at this point of time was y, okay, and this distance was some x, okay, or let's say this was x naught and this was y naught, and this started moving like this, this started moving like this. So after some time, what we'll observe is that now in comparison to earlier, this block has moved down a little. So you can see that in this diagram, this pulley with the block A attached to it is moved down by some delta y, let's say. Okay. And during that same time, this block has moved here. So let's say earlier it was here. So this block during this time has made a displacement of delta x. So this length from here to here has become x now, which is the initial value minus delta x. Okay. And this total length from here to here now has become y, which is y naught plus delta y. So this is at some time t. This was at the initial time t equal to 0. You can see that this block also was here earlier and now it's moved down like this. Now what should happen between these two pictures? The total thread length should be conserved. Okay, so the total thread length here should be conserved. So that will show here that whatever the initial thread length was L. Now here what is happening on the vertical side, the thread length has increased by delta y plus delta y. So plus 2 delta y. Whereas this section, the thread length has decreased by delta x. So that shows us that 2 delta y minus delta x should be 0. So that shows us that the horizontal displacement of block B should be twice of the vertical displacement of block A. This is the constraint relation, that the horizontal displacement of block B is always equal to 2 times the vertical displacement of block A.
So I couldn't get that part. Like, how do you came to that equation L equals to L plus 2 delta y minus delta x?
Yeah, so compare the thread length on the left hand side, the blue colored one, with the thread length on the right hand side, the red colored one, and you'll understand this. This total thread length, the vertical branches have increased by delta y and delta y. No? So there's plus 2 delta y. Whereas this horizontal sections, it's reduced by delta x. So there's minus delta x. Is it clear now?
Yes, sir.
So this is the relationship between their displacements. So this is called the constraint relation. And this constraint relation is coming from the fact that the thread length is conserved.
Or what you have written after L plus 2?
2 delta y minus delta x. Okay, so now the thing is, if we differentiate this relation,
Sir, once again.
yeah, I've explained earlier also how the thread length equation came. Just follow the diagram on the left hand side and the right hand side. So the total thread length is the horizontal branch plus the two vertical branches. Now on the right hand side, the horizontal branch has decreased by delta x, whereas the vertical branch has increased by 2 delta y. So the total thread length is like this now. Okay, understood this now. Okay. Now differentiating this relation, we will get velocity of B is equal to 2 times velocity of A at any time, because velocity of B is rate of change d by dt of SB, and velocity of A is the rate of change of SA. Okay. And then differentiating that one more time, we'll get that acceleration of B is 2 times acceleration of A. So this is the constraint relation between the two. And now once we have seen the constraint relation, the rest of the things become easy because we can just understand the free body diagrams. This is moving with an acceleration like this. This is moving with an acceleration like this. Now on this, there is a horizontal tension T. On this, there are two vertical tensions T. So when you look at the free body diagrams, you see that on B, there's tension T and horizontal acceleration EB. So T is equal to mass of B into EB. That's our second equation. This is our first equation. Whereas on the block A, see that through the pulley, there are two tensions which are acting upwards and is having a downward acceleration E like this. So we have weight minus 2T is equal to mass of A into acceleration of A. This is our third equation. And now solving equation 1, 2, and 3, you can get the acceleration of A and the acceleration of B.
Done, sir.
Okay, so what we can now do is we can substitute the value of tension from here in this equation. So this will become rate of A minus 2 times mass of B into acceleration of B is equal to mass of A into acceleration of A. Then we can substitute this over here. So this becomes rate of A minus 2 times into 2 times acceleration of A. Further, this equation becomes mg for A is equal to ma plus 4 mb when we carry this that side into acceleration of E. So acceleration of E will get a value of this much. Whatever the mass is, we can substitute and get values. And acceleration of B is obviously double of acceleration of A. So once we get that, we can solve this.
Sir, what was the equation 1, 2, and 3? Can you scroll up?
Sorry, come again.
Can you scroll a little bit up?
Yeah.
Yes, sir. Noted it. So can you scroll a little bit down?
Okay, so understood this equation now how it came. We differentiated this equation on both sides. So displacement's derivative becomes velocity. That's how we got this. And then we again differentiate this one more time because acceleration is equal to rate of change of velocity. So we differentiate this one more time. So then we get this. Okay. So this gives us the relation between the two accelerations. If the displacements are happening in 1:2 ratio, then velocity will also be in 1:2 ratio, acceleration will also be in 1:2 ratio. So that is our first equation, which is the constraint relation. Then we are getting the next two equations from the free body diagrams. Okay. So hope this is clear to all of you. With this, we conclude today's session. So I'll be sending you a list of questions to do from HC Verma and from the module, which are related to Pulley systems and particularly to constraint relation type of problems. Okay. So wish you all the best. That's it for today. Have a nice day, people.
So can you explain the last part?
Which part, beta?
Sir, that's substitution.
Substitution I've written. It's very clearly. See, second equation में t का value जो है हमने क्या किया है? Third equation में substitute किया है. So t को replace कर दो with mb into ab. So see, we got this equation now. Understood now?
Yes, so can you scroll down? Then I will copy
And
this.
then after that, what we have done, see, after that we have substituted from the first equation the value of AB as 2 times the value of acceleration of A. Okay, so that's the next substitution. So now we substitute this over here. So this equation now becomes this. Understood? So it's a two-step substitution, right?
Yes, I got it. Got it.
Okay. Okay, so you can complete noting this down, and that completes today's session. Wish you all the best, people. Have a nice day.
So, bye, sir.
Bye, people. Bye.
Bye, sir.
Bye, sir. Thank you, sir.
Excuse me, sir.
Yes, beta.
So could you please send the recording on the non-integrated group for the first 15 minutes?
Yeah, but I'll send the entire recording. Okay, and I'll send that will have the first 15 minutes also.
Okay, thank you, sir.
Okay, you understood that question, na? The first one that we were doing, where
Yes, sir.
there was a heavy rope and the light string.
Yes, sir.
Okay, so then you will not have any problem with the first 15 minutes. Beta. That's what we were discussing.
Oh, okay, sir. Thank
Okay, beta. All the best.